All right, let's talk about increasing and decreasing functions. Let's start off with some basic examples. I'm going to show here a few coordinate planes, and hopefully we understand that if a graph goes up from left to right, that it's considered increasing. And so let's do a few examples here. And we can clearly see on each one of these as I go from left to right, my y values are increasing, or the graph is going up. So even something that looks like this. So all of these are examples of increasing functions. Likewise, we could discuss decreasing functions in the same way. We would say if the graph goes down from left to right, then we would have decreasing functions. So here's our increasing. Let's get some decreasing on here. So here's a decreasing function from left to right. The graph goes down. Got a linear function there. It's decreasing. So all these are decreasing functions. Okay. We discuss increasing or decreasing in terms of intervals of the domain. Okay, those are our x values. Okay, so now let's look at this graph. And we can see that we've got some interesting curves here. And we want to start talking about the portions of the graph that are increasing, that is going up from left to right, decreasing, and constant. Let's make this a little bit more careful here. Okay, while we were paused there, I was redrawing this. It seems my pen was not calibrated. Anyhow, we can start discussing intervals of where we are increasing, decreasing, or constant. And so as I trace my graph from left to right, I am clearly increasing. We're talking about for the x values from negative infinity all the way to -4. So we can start talking about the intervals of increasing and decreasing. So I'll say it's increasing over the intervals. Remember, these are intervals of the domain from negative infinity, right? The x value is negative infinity all the way to -4. And then let's look again and see where else are we increasing. So my graph is going up from left to right from the interval 4, and it looks like to 5. Okay, now we can do the same thing, and we can talk about it where it's decreasing. And so where is my decreasing? Well, it's decreasing. I'm going down here from -4, looks like, to -1. And then let's trace some more. Here we are decreasing again from 5 to infinity. Okay, and then there's one other section where it appears that we are constant, right? The y value is not changing. So I'm going to change that to green. The function is constant over the interval, and it's again the x values that we talked about, the domain from -1 to 4. Okay, well, we're getting into discussions about calculus now, because this kind of thing was stuff that maybe you did in college algebra, previous course. But now we are looking at calculus, and let's see what we can come up with here. Perhaps I draw a line tangent to this curve. So I'm going to put a dot here, and let's hope that I am better calibrated. And I'm going to draw a line, a tangent line. Oops. There we go. Okay. And if we were talking about that tangent line, I hope you could look at it and you could see that the slope of that tangent line would be positive, right? This slope would be positive. And perhaps I go to this other side, or I could even go right here. These look very similar. I just want to give myself some more space. And let's say I draw a line tangent to the curve at this point. And now I see that this line would have a negative slope. Okay. Now, what if I pick either right here, I hope you can see that, or right here, and I try to draw a line tangent to the curve? What can I say about its slope? Well, it's a horizontal line, and its slope is 0. Okay, what if I went in and I went to this portion of the curve, right here, and I tried to draw a tangent line? Well, its slope would also be positive. Or maybe I go back over here, and I can notice that the tangent line slope would be negative. And if you're starting to notice, this is the portion of the graph where we are increasing. So when I am increasing on my function, the slope of the tangent line seems to be positive. Where my function is decreasing, the slope of my tangent line is negative. And I can see here that where I am changing direction, right, going from increasing to decreasing, the slope of this tangent line is 0. And so this is where calculus comes in place. We call it the first derivative rule. We can start making some conclusions and drawing some connections. And if you remember, the slope of the tangent line is given by the derivative, right? So I'm going to have not only that m is greater than 0, but this is f prime of x, right? And over here I can say f prime of x. And over here I can say f prime of x, right? So using the function its derivative, we're going to determine where our function is increasing and decreasing. Remember, we do get graphing calculators, but it's not always something that's easy to get the window on your calculator appropriate so that you can see everything that's happening with your function. And also, we're really just building connections here and being able to logically reason through and work through these types of problems. And let's assume that we don't have access to a calculator. Sometimes it's nice so we can check our work, but we're really going to have to show all these things by hand. Okay, so this is a good place to summarize what we've shown here. We're saying if our derivative, or f prime of x, is positive, greater than 0, that means our function is increasing. And if f prime of x is less than 0, or it's negative, as we're seeing here, then our function is decreasing. Okay, where the slope m, or f prime of x, is equal to 0, that means our function is changing direction. Or it could be that we're talking about over an entire interval, or the function then is constant. Okay, we need to be careful on this. We don't get too in-depth in this course. But this is when we were talking about over an entire interval. Okay? Okay, we have a special name where the derivative can change from a positive to a negative, or from a negative to a positive. And that x value where that occurs is called a critical number. So I've written a little note here, if you want to add it to yours. F prime can change from positive to negative at points where f prime of x is equal to 0, so like we saw here. and at points where the derivative does not exist. And these values of x are called critical numbers. Okay, in particular, we say where f prime of c equals 0, or where f prime of c does not exist, c, which is just being substituted as an x value, c is called a critical number. So we may be asked to find critical numbers in the interval where f is increasing or decreasing. So let's take an example. So find critical numbers in intervals where the function f is increasing or decreasing. First example, the function f of x is equal to negative x cubed minus 2x squared plus 15x plus 10. Okay, so I'm supposed to find critical numbers, and I need to find where f is increasing and decreasing. But I just found out that critical numbers are where my derivative is equal to 0 or where it doesn't exist. And if I can figure out where the derivative is positive, then I know my function is increasing. And if I figure out where the derivative is negative, my function is decreasing. And all I have to do is go back up to my notes here and just see that where my derivative, right, my slope of my tangent line is negative, my function is decreasing. My function is increasing when my derivative, or my slope of my tangent line, is positive. Okay, so in order to solve these, I am first going to find the critical numbers, and then I'm going to test around them to see where my function is increasing and decreasing. And so I kind of do the same setup every time. I am working with a polynomial, so I know that my derivative actually is going to exist. Again, I don't have to worry about where it does not. So really my critical numbers are just going to be where the derivative is equal to 0. So I take the derivative, and by this time I'm very quick at it. Negative 3x squared minus 4x plus 15. And I say, okay, let's find the critical numbers. I'm going to set f prime equal to 0, or see where it doesn't exist. Of course, here again we're talking about a polynomial, so I don't have to worry about that. But I remember that for future cases. And then I'm going to solve for those x values, and whatever those x values are, those are my critical numbers, right? So I'm going to set this equal to 0. And why not factor out that negative? And this is where it comes in handy to be able to factor quickly. I could use the grouping method if I want. Just as a side note, if you're doing like a grouping method, or you might call it like the AC method is probably what you've heard of, we're going to look for numbers to rewrite this that multiply to 45, negative 45 that is, because 3 times negative 15 is negative 45, and they're going to add to 4. And so I'm going to go off to the side and show this work. So I rewrite the first term, and I'm looking for the middle term that's going to add back up to 4, and these two numbers product would be negative 45. And so if I think about it, 9 and 5, and one of them has to be negative, and that's going to have to be 5. Right? I'd multiply these together, I get negative 45. I add them together, I get positive 4. And so I can begin to factor. And I could group this term, and I can group this term. I factor out the common factors. And so this would factor, and perhaps I could have done this by guess and check, but it doesn't hurt to show this method. So I would factor this quadratic then into the quantities 3x minus 5 and x plus 3. And so we have the zero factor theorem. It says the only way that this will multiply to get this product of 0 like it says we're looking for, because remember that's what it says our critical numbers come from, where first derivative is equal to 0 or where it doesn't exist. So we're only worried about here in this case this polynomial where it's equal to 0. So it says I'm going to figure out what x value makes this 0, and I'm going to get x could be -3, or I'm going to get that x could be, looks like 5/3, right? So these are my critical numbers, which I've only solved part of this. Right, these are the critical numbers. I need to solve the other part that says find where our function is increasing and decreasing. And so what we do after this, it's kind of the same thing every time. I draw a number line. I put my critical numbers on that number line. So -3 would be back here, 5/3 over here. And then I'm going to try to figure out what's going on with the derivative, what the sign is, because if the derivative is positive, then I know my function would be increasing. If my derivative is negative, my function is decreasing. And so what I want to do is test, and I can do that with a sign chart, basically. And so I'm going to test something within the left side of -3, so how about -4? And I'm going to test something between these two x values, so how about let's test 0. And let's test, let's see, 5/3 is 1 2/3, so let's test x equals 2. And so what I'm doing is I'm going to plug in to my factored form of my derivative. And if you recall, my factored form had negative quantity 3x minus 5 times the quantity x plus 3. What I'm going to do is I'm going to plug in each one of these x values and determine what the sign is of my derivative, and that's going to tell me if my function is increasing or decreasing, right? It's based off of what my derivative is doing. It's the first derivative test, really. Okay, so if I plug in -4, what I note is that there's already a negative sign on the outside. If I plug in -4 into the set of parentheses, it's not so much what the number I get, it's the sign. So I go 3 times -4, it's going to give me a -12. -12 minus 5 is a -17. I only really care about the negative. If I plug in -4 to the second set of parentheses, so it'd be -4 plus 3, I get a -1. And so I go a negative times a negative is a positive times a negative is a negative. So I get an overall negative. That tells me that f prime is negative for the interval for anything I would test back here, like -5, -100, -1 million. It says my derivative would be negative. Now if I recall, derivative being negative, that would mean that I would have excuse me, a line with that negative slope, which meant that my function was decreasing. So over that entire interval, my function is decreasing. Now let's do the same thing if I test x to be 0. Well, there's a negative sign on the outside, so I put that down. If I plug in 0, 3 times 0 is 0. 0 minus 5 is a negative. If I plug in 0 to the next set of parentheses, 0 plus 3 is a positive. So I'm going to get a negative times a negative is a positive times a positive is a positive. And so my derivative would be positive, or the slope of that tangent line is positive on this interval, anywhere that I choose between here. And so that means my function is increasing, right? A positive slope meant my function was increasing. I can rewind, or if I want to on mine, I can scroll back up and I can see exactly what we're talking about, slope of that tangent line being positive. Okay. I'm going to do the same thing if I test x to be 2. My function has a negative on the outside here, and now I start plugging into the parentheses. Factored form helps a lot. If I plug in 2, I'll have 6 minus 5, that's positive. 2 plus 3 is positive. So negative times a positive is a negative, negative times another positive is a negative. So it looks like my derivative, or the slope of the tangent line, is negative, and that meant that my function was decreasing. So I've, pardon the loud noises there, but I've found my critical numbers. They're actually located right here. They assist me in creating my number line, and I'm going to test on either side of those. So for the rest of this problem, I'm going to say that my function is decreasing, and I'm going to provide those intervals. It was anywhere that was to the left of -3, so I'd be from negative infinity all the way to -3, and then it looks like from our chart that we have that it's decreasing from 5/3 to infinity. And we would say that it's increasing over that interval that we see here, right? Increasing from -3 to a positive 5/3. And so this is how you're going to approach the problems. Every time you're going to first find the critical numbers. How do I find critical numbers? Well, I'm going to take the derivative and set it equal to 0, or I'm going to, and I'm going to check to see where the derivative doesn't exist. So those will be my critical numbers. Those are my x values where my derivative is equal to 0, or where it doesn't exist. I plot those on a number line, and then I test points on either side to see what's happening to my derivative. If my derivative is positive, then my function f is increasing. If my derivative is negative, that means my function f is decreasing. Okay, let's do another one. Same set of instructions. What we're going to do is find the critical numbers and find where our function is increasing or decreasing. And so we have the cube root of the quantity x minus 1, which is squared. Okay, and so I'm going to find where the function is increasing or decreasing, and I want to know the critical numbers. So the first thing I do is find the critical numbers. In order to do that, I'm going to have to take the derivative. I'm realizing, hopefully at this point, that I should probably rewrite this so that this is x minus 1 raised to the 2/3. Right, this is still my function f, and then when I take the derivative to find the critical numbers, I can then use the chain rule. So this would be 2/3 times the quantity x minus 1. I subtract 1 from 2/3, so that gives me -1/3. And then you're supposed to multiply by the derivative of this inside function, and the derivative is just 1. So it looks like we have it. Okay, so let's rewrite this. So I'm rewriting this without the negative exponent. So this is going to be 2/3 times the quantity x minus 1, which is raised to the 1/3, or I could write that as the cube root. Right, that would be the same thing right here. Okay, so I'm going to find the critical numbers by setting the derivative equal to 0, or by finding where it does not exist. Okay. Anytime you have a rational function, that means that we have essentially this fraction, we have in the denominator a variable, we should start thinking about domain and that we cannot divide by 0. So actually, where would my derivative not exist? It would not exist where the denominator is equal to 0. So let's go 3 times the quantity x minus 1 raised to the 1/3. Let's set it to 0. Because we cannot divide by 0. I'm not taking the derivative and setting it to 0 right now. I'm saying where would my derivative not exist? And if I go through solving equations with radicals, what you do is you isolate your radical. So I could divide both sides by 3. Well, 0 divided by 3 is still 0. So I have the cube root of the quantity x minus 1 equals 0. And then what you do is you raise it to the power of that index. So this is a cube root, so I'm going to cube it. So I'll have x minus 1 equals 0. So it looks like where x is 1, I'm and I could probably have done that right away, but where x is 1, that's where my derivative does not exist. So this is all where f prime does not exist. That's where the denominator is 0. Okay, so I have one critical number. And we should put exclamation points because we're really excited about that. But I'm also supposed to check where the derivative doesn't exist. Excuse me, where the derivative is equal to 0. I just did where the derivative doesn't exist. So let's look over here. We've done this case. Give myself some space. And now I'm going to set f prime of x equal to 0. All right, that's where I'm supposed to check for critical numbers. So I say 0 would equal 2 over 3 times the quantity x minus 1 to the 1/3. And hopefully I've realized that this is a fraction. No matter what x value I plug in here, and of course I don't want to plug in 1, that's what doesn't exist, I will always have 2 divided by some number. 2 divided by 3, 2 divided by 5, 2 divided by 500. And with this constant sitting in the numerator, anything I plug into the bottom, I'm just going to have a fraction, and that fraction will never equal 0. Okay? We will never be able to plug in an x value and have this right-hand side evaluate to 0. And so f prime will never equal 0. So I don't get actually a critical number from performing take the derivative and set equal to 0 because it will never equal to 0. And maybe pause and think about that for a few minutes. But 2 divided by anything is just going to be a fraction. It could be really small, it could be really large, depending on what we're putting in here. But it will never equal 0. So it looks like my only critical number comes from what we did initially, and that was me just kind of paying attention and noticing that, hey, I'm working with a rational function here, and my denominator I can't divide by 0. So we've only got one critical number, but then I go through the motions and I say, well, critical numbers, what I do right away is I stick those critical numbers, in this case just 1, on a number line, and then I'm going to test to the left and right. So let's test 0, and let's test 2, perhaps. This would be easy. And I fill in that I'm going to think about what's happening to f prime, because that will give me information about f of x. And I usually take a factored form. In this case, there's nothing really any easier than what was given to us. We have that the derivative was 2 over 3 times quantity x minus 1 to the 1/3. Or I could put the cube root here if I want. And I'm just simply plugging in these x values, these tests, to see if the derivative is positive or negative. Again, if the derivative is positive, my function is increasing. If the derivative is negative, my function f is decreasing. So if I plug in x to be 0, I have a positive 2 in the numerator. That's going to stay. If I plug in x to be 0, I will be taking the cube root of 1, right? 0 minus 1 is going to be negative 1. So I'm taking the cube root of negative 1, which is negative. So I have 3 times a negative, so I get a negative on the bottom. Positive over negative is a negative. So my derivative, f prime, is negative, which means that my function is decreasing over anywhere on that interval to the left of that critical number, x equals 1. And then I do the same thing when x is 2. So the numerator is going to stay that positive. If I plug in x to be 2, I'll have 2 minus 1. So I take the cube root of 1, that's positive, and a positive times a positive is a positive. I've got a quotient of a positive over positive, which is also positive. And so I have that our function is increasing over the interval. And so to answer this, my critical number is x is equal to 1. Where is my function decreasing? It looks like my function f is decreasing anywhere from negative infinity to positive 1. And then we would be increasing, as we showed here, from 1 to infinity. And that, overall, those are pretty good examples to get you started. Always look for your critical numbers first. You find those by taking or solving where f prime is equal to 0 or where it doesn't exist. You place those on a number line and you plug into your first derivative, testing to see if it's positive or negative. Shouldn't be much to memorize as far as that first derivative rule because it's intuitive if you start graphing and thinking about what the tangent line would look like.